Hello friends, in this video I will be covering the topic of hierarchical clustering. This is the second clustering technique we will be discussing after my previous video related to k-means clustering algorithm. Similar to k-means, hierarchical clustering is a technique used in data mining to group similar data points together. The unique way it works is that it creates a hierarchy of clusters, which can be visualized as a tree-like structure called a dendrogram. There are two types of hierarchical clustering methods, agglomerative and divisive. In agglomerative clustering, initially each object is considered to be its own cluster. According to a particular procedure, the clusters are then merged step by step until a single cluster remains. The divisive method is the opposite of the agglomerative method. Initially, all objects are considered in a single cluster, then the division process is performed step by step until each object forms a different cluster. The cluster division or splitting procedure is carried out according to some principles that maximize distance between neighboring objects in the cluster. Here is an example of hierarchical clustering. Each point represents a student's scores in English and algebra. As we can see, there are multiple ways of clustering the students together. For example, Demi and Nash can be clustered together as they are very close to each other. Further, they both and Catherine can be considered another cluster. The three, along with Henry and Anna, can form another cluster, and so on until we have a single cluster containing all the data points. The following are a few examples of the real-life application of hierarchical clustering. In bioinformatics, it is used for grouping animals according to their biological features to reconstruct phylogeny trees. In business, we use it to divide customers into segments or forming a hierarchy of employees based on salary or other characteristics. In image processing, we can group handwritten characters based on the similarity of the character shapes. And in information retrieval, we can use hierarchical clustering for categorizing search results based on the queries. The following are the advantages of hierarchical clustering algorithm. It is easy to implement and understand. There is no need to pre-specify the number of clusters. Instead, the dendrogram can be cut at the appropriate level to obtain the desired number of clusters. It is deterministic, meaning more predictable. And finally, the outliers can be detected with the help of the dendrogram. There are also certain drawbacks of the hierarchical clustering algorithm. It is not suitable for large data sets since the computational cost and time is higher. It finds difficulty in handling different sized clusters. We'll come to know more on this when we discuss the DB-scan algorithm in the next video. And finally, the hierarchical clustering algorithm is sensitive to outliers and noise in the dataset. Hierarchical clustering employs a measure of distance, a proxy for similarity, to create clusters. Between agglomerative and divisive clustering, agglomerative clustering is the preferred method. Steps for agglomerative clustering can be summarized as follows. Step 1 is to compute the proximity matrix using a particular distance metric. In step 2, each data point is assigned to a cluster. Step 3 merges the clusters based on a metric for the similarity between clusters. The distance matrix is updated in step number 4. And then we repeat steps 3 and 4 until only a single cluster remains. The first step of the algorithm is to create a distance matrix. The values of the matrix are calculated by applying a distance function between each observation. Euclidean distance function is commonly used for this purpose. The structure of the proximity matrix will be as shown in this image. For a data set with n elements, here d pi pj represents the distance between 2 points pi and pj. There are various methods of computing similarity between clusters in order to combine clusters to form larger clusters. A numerical example will help illustrate the methods and choices. We'll use a small sample data set containing just 9 points in a two-dimensional space as displayed in this figure. Let's suppose we have two clusters in the sample data set as shown in this figure. One way to measure the distance between clusters is to find the minimum distance between points in those clusters. That is, we can find the point in the first cluster nearest to a point in the other cluster and calculate the distance between these 2 points. In this figure, the closest points are P2 in cluster 1 and P5 in cluster 2. The distance between those points and hence the distance between clusters is found as d p2 comma p5, which is equal to 4. Another way to measure the distance is to find the maximum distance between points in two clusters. We can find the points in each cluster that are furthest away from each other and calculate the distance between those points. In this figure, the maximum distance is between point P1 and P6. The distance between these 2 points and hence the distance between the two clusters is found as d P1 comma P6, which equals 10. The advantage of the maximum or complete linkage method is that it is less sensitive to noise and outliers in comparison to min method. Its disadvantage is that it tends to be biased towards larger clusters. The centroid method defines the distance between clusters as being the distance between their centers or centroids. After calculating the centroid for each cluster, the distance between those centroids is computed using a distance function, example, the Euclidean distance function. The average method defines the distance between clusters as the average pair-wise distance among all the pairs of points in the clusters. For simplicity, only some of the lines connecting pairs of points are shown in this figure. If I show you all the connections, the chart will become very cluttered. The Ward approach analyzes the variance of the clusters rather than measuring distances directly, minimizing the variance between clusters. With the Ward method, the distance between two clusters is related to how much the sum of squares value will increase when combined. In other words, the Ward method attempts to minimize the sum of the squared distances of the points from the cluster centers. Compared to the distance-based measures described above, the Ward method is less susceptible to noise and outliers. Therefore, Ward's method is the preferred method for linkage in hierarchical clustering. Silhouette score is the evaluation criteria for any clustering approach, including hierarchical clustering. Its calculation is as follows. Intra-cluster distance A measures the average distance between data points within a cluster. Nearest intercluster distance B measures the distance between a data point and the closest data point in the nearest neighboring cluster. Silhouette coefficient is calculated as B minus A divided by max of A or B. Its interpretation is as follows. A value of plus 1 represents the ideal case, indicating a data point is well matched to its own cluster and poorly matched to its nearest neighboring cluster. A value of 0 indicates that the data point sits on or very close to the border between two clusters, making it difficult to determine its clear membership. And a value of minus 1 represents the worst case, suggesting the data point was likely assigned to the wrong cluster and has a higher average distance to its own cluster members compared to the nearest neighboring cluster members. The following are the similarities between the k-means and the hierarchical clustering methods. Both the algorithms fall under the class of unsupervised learning. Both algorithms work with unlabeled data. They learn the underlying structure of the data by identifying groups based on their similarities or distances. In terms of clustering objective, both algorithms aim to identify groups or clusters of data points that are similar to each other and different from points in other clusters. And both the algorithms are distance based. They rely on distance metrics to measure the similarity or dissimilarity between data points, guiding the cluster formation process. In terms of differences, the number of clusters are predefined by the user in k-means, while hierarchical clustering algorithm can discover the appropriate number of clusters automatically. In k-means, the clustering approach is based on the centroids, while hierarchical algorithm builds a hierarchy of nested clusters, progressively merging or splitting the clusters based on their similarity. In k-means, the interpretation of clusters could be a challenge, particularly for more than two-dimensional dataset, while hierarchical clustering provides a visual representation, that is a dendrogram, which helps visualize the hierarchy and relationships between clusters, allowing for easier interpretation of cluster structures. Further, k-means is less sensitive to outliers. It doesn't explicitly consider outliers in the initial centroid placement, potentially leading to less drastic impacts. While in hierarchical clustering, outliers can significantly impact the merging or the splitting process, potentially leading to distorted clusters. Finally, k-means typically performs well with large datasets due to its iterative and efficient nature, while hierarchical clustering can become computationally expensive for large data due to the need to calculate distances between all data points in each step. Let's perform hierarchical clustering on a real-world dataset to solve a real problem using Python. Here, we use a dataset from the book Biostatistics with R, which contains information for 9 different protein sources and their respective consumption levels in various countries. We'll use this data to group countries according to their protein consumption. Let's now switch to the Jupyter Notebook. I have provided the link to my Jupyter Notebook on GitHub in the description section of this video. We start by importing the required libraries. This command directs matplotlib to display generated plots directly within the notebook itself in line with the code cells that produce them. This code snippet imports functions for performing hierarchical clustering and accessing cluster information from the SciPy cluster hierarchy library in Python. This function creates a visual representation of the hierarchical clustering process known as a dendrogram. This function performs the core hierarchical clustering algorithm. It takes your data and a distance metric as input and returns a linkage matrix that encodes the merging process of data points into clusters. This function allows you to assign data points to specific clusters based on a given linkage matrix and a threshold value. This line imports the NumPy library as NP. NumPy is a fundamental library for scientific computing in Python and is often used alongside SciPy for data manipulation and mathematical operations. This command loads a CSV data file available online. Data.head command displays the first 5 rows of the newly created data frame data. This is a common practice to quickly inspect the contents of a dataset and get a sense of its structure and data types. We'll first store the features for clustering in X2, which are contained in all rows and columns from 1 through 10. This code creates a new variable X2 that contains a subset of the original data frame DF. It includes all rows but only selects columns from the second to the ninth columns. We use the linkage function for clustering the data. This code performs hierarchical clustering on a data set using Ward's method and Euclidean distance metric. Finally, we can plot a dendrogram of the Ward linkage clustering of 25 countries based on their protein consumption. From the dendrogram, we can observe two distinct clusters colored green and yellow. This result indicates that countries in each cluster get their protein from similar sources. Using the FC cluster function, we can find and add the cluster labels for each country to the data frame. There is a code to do it much faster. This code utilizes the scikit-learn library for performing agglomerative hierarchical clustering and then prints the assigned cluster labels for each data point. Thanks friends for watching. If you found this video useful, please hit the like button and also subscribe to my channel for upcoming videos. Bye for now.